Welcome to this Frequency Matters podcast. I'm Pat Hindle, and I'm here with my co-host Eric Higham. And today we're talking with Darren McCarthy, Aerospace and Defense Industry Segment Manager at Rohde Schwarz. Welcome, Darren.
Well, thank you. Thank you for having us on.
So I've always been very intrigued with Rohde Schwarz mmWave security scanners and how they were being used in airports and other security applications. So I know that the company last year won a $11 million award to the TSA to supply millimeter wave security scanners to U.S. airport security screening checkpoints, and that was after the TSA qualified them in 2022. So can you tell us what is expected for the rollout of scanners in the U.S. and Europe?
Oh, sure. Yeah, as you mentioned, we had last September we got a TSA contract award, and this is after a long qualification period. We're actually certified back in 2018, and we've been deploying several systems in a limited quantity at many airports around the U.S. So right now, major news is we had the Denver Great Hall project finally opened earlier this month, and there's 17 lanes of security scanners in that project. Other than that, we've also been installing in LaGuardia, Newark, Las Vegas, LAX, Houston, Fort Lauderdale, and several other airports. The TSA contract specifically, where those programs were purchased by the airports and the airlines, the TSA contract is directly federally funded. And that's going to be put and rolled out into places over the next couple months. And right now we know of, Austin, Clovis, New Mexico, Cincinnati, Detroit, and Grand Rapids. There are about 240 airport projects, many of them doing security upgrades right now. So there really is a lot of upside opportunity for new security systems. Internationally, we've had our European equivalent of the TSA, the ECAC approval, for several years now. And throughout Europe, Asia, South America, and the Middle East, we have well over 1,000 systems in over 100 airports, including all the ones in the UK, Amsterdam, the Schiphol Airport, and many in Germany as well.
Well, if we can dig into the details, that's a great overview. Thanks for that. The system requires only a few milliseconds to scan passengers, and it seems like it's easy to use. How does the millimeter wave scanner work to image objects on a person, and how accurate is it?
Great. So, yeah, we usually don't have customers that request the technical details, but I'm glad we have interest in this community here. The system really has two flat panels and basically operates as a low power multi-static radar. Each of the panels, front and back, have 3008 transceiver pairs. And basically, one is transmitting a very low powered CW signal below a milliwatt, while the other 3000 plus sensors on a wall are receiving the reflection and processing the information. And so, because of the angle of the reflections you get back, you basically get a three-dimensional volume of response. It transmits a CW frequency and then steps through 160 different CW frequencies over a 10 gigahertz span and then moves on to the next transmitter. So it's doing this 160 signals times 3008 times 2. And it's doing this about 5 times faster than a blink of an eye for both panels to operate, about 32 milliseconds each. So for a total of 64 milliseconds. The processing power of that image is well over 28 teraflops of information. And the resolution that you're able to get out of this is basically a 2 millimeter square, which is the size of a match head.
Wow, that's great resolution and some serious processing power, a lot of data. And so, what other security applications are these systems being used in, as it seems like they would work in many different places?
Yeah, I like to say we're primed for the applications where a metal detector just won't work. So in the aviation industry, obviously you have passenger screening. There's also new mandates that really haven't been disclosed to industry, but for aviation worker screening as well to get into the sterile area. And those are being implemented over the next several years. We actually have two different systems. I'll talk about the other one later on, but we have a portal system, which is basically where you stop and pose, for passenger screening. And we also have a walkthrough technology that we'll talk about a little bit later. But between these two systems, we've deployed them in correctional facilities, pharmaceutical manufacturing, cosmetics, critical infrastructure, component manufacturing, data centers, customs and border security, cruise liner entry, embassies, courts, and even event screening, concerts and soccer matches. And each of these, there's the sense that if you think about things that a metal detector can't see, and I bring up the analogy of the soccer match, the events, they're not worried about, they're not actually worried about knives, or wallets or keys. They're worried about bottles and pyrotechnics, people setting off smoke bombs and things like that, because that can basically cause a home team to lose a match, if they get disqualified. And so other applications for the scanners are looking for drugs, money, powders, data bearing devices, 3D printed weapons, and a lot of things that you just don't get with a metal detector. The other thing is we're able to train our systems on objects using machine learning, AI, and deep learning. And this really allows us to address a lot of tailored markets. And so typically, if we have a customer application where they're looking for a very specific item to be disappearing, we have done this in the area of cell phone manufacturing parts, as well as powders from a specific manufacturer. And we were able to train on those different items and optimize the algorithms for that specific item.
Yeah, thanks. So you just mentioned a number of applications other than that airport security. And so what are the advantages of millimeter wave scanning versus X-ray technology?
It really comes down to safety and perceived safety. Backscatter X-ray, is a technology that was rolled out about 15 years ago in the U.S. after the failed underwear bombing, and that was used for a short period of time before some studies really about the use of ionizing energy were kind of made the public straight. And it's not so much the exposure that an individual getting scanned, the levels and the doses are really low, but the concern was about the operators who are sitting there for thousands and thousands of scans a day and not really being offered much protection. And this, in fact, that X-ray technology for use on people, I mean, right now it's used on baggages extensively, but for use on people, it's starting to become outlawed in the state by state. There are several states that have forbid the use of it on people. And really it comes down to X-ray technology is ionizing and can penetrate the skills and potentially do damage to cells, where millimeter wave and the frequencies that we're using are non-ionizing, and they actually bounce off the cells, bounce off the skin, and do not penetrate the skin. So it really is a concern of safety.
Yeah, it's very interesting, and the resolution is spectacular, so that's good. So let's get a little bit into, the design and development. What were some of the challenges that you had to overcome in this type of system? Because it's a lot of antennas and a very high frequency, so I can imagine it was complicated.
Well, being a microwave and millimeter wave company, there are a lot of challenges with the level of integration that had to be achieved in the millimeter wave design. And we collaborated with industry, semiconductor industry, in designing custom chipsets to be able to create this multi-static operation. And really, this has allowed us to come up with basically a design that's proved some longevity, that we've been able to utilize the same kind of front end design while taking advantage of Moore's law in the background. When we first had our first imaging technologies in the lab, proof of concept, I believe I heard that the first images of the body scanner on a single wall took about 7 minutes to process the image with the best computation power available, in the late 2000s. When we started getting certified for use in ECAC, the European and TSA back in toward the mid 2015, and I say certified as opposed to qualified because the two are very different things. Scan time and processing time. The scan time doesn't remain the same at the 64 milliseconds, but the processing time then dropped down to about 7 seconds. And today, we're really able to take advantage of being able to do the processing with the latest and greatest GPU processing. We're down just over a second to be able to do those 28 teraflops of information. The other big challenge was the development and continued development of deep learning algorithms. Threat objects and as well as clothing. If you think of the different clothes that people wear culturally, as well as religious dress, a lot of the systems that are fielded today have trouble with fit clothes and different types of clothes. So being able to train our algorithms and make them gender neutral, as well as be able to take advantage of understanding the different clothing models that people might have, has allowed us to significantly reduce the false alarm rate of our technology. And while you can't take these files of people and use them when it's a fielded operation, there, because of privacy concerns, there is no image capture in the field. This is primarily done in an R&D mode in the lab with the consent of the people being scanned. And coming from a company with over 10,000 people, willing to volunteer, we're able to develop a lot of these models and have those for use in our deep learning capabilities going on in the future. So building that library for AI and deep learning was really another big challenge that we worked on, and it's basically taken, we're over 15 years into this project.
Yeah, that's interesting, and certainly it sounds like the silicon processing and the algorithm development was pretty critical to this whole thing. But if we switch focus just for a second and look at the RF side of things, what frequencies are you using? And earlier you mentioned a resolution of 2 millimeters. Is that sort of the nominal? Is that the best? Is that run of the mill?
Oh, good question. People often mistake resolution with detection capability, and so the resolution is really the size of the object that you can see. And I think there's a test pattern. Actually, there's an IEEE standard being written right now around image quality. And basically, if you put a ruler, and with circles and squares and stuff like that, the resolution is basically how small of an object can we resolve. And the 2 millimeters, basically the size of a rivet of a gene, but to determine is that rivet of a gene a threat object, you need more than 1 pixel of information to be able to see that. So detection level and detection capability is a good thing, and the TSA holds their detection requirements very strictly secret. So let's just say we've met the highest levels that they're able to test right now. The QBS frequencies that we use for the 201 is between 70 and 80 gigahertz. So that's really the 10 gigahertz span at which we operate. And we have a sister product using that same technology called the QAR, which is used in the automotive industry to test the alignment of the radomes in the ADAS systems, driver assist systems. We have another technology I mentioned earlier, which is a walkthrough technology. And that uses basically an ultra wideband pulse in the 3 to 11 gigahertz range. And we use that as a separate frequency because of the excellent RF penetration capabilities. It's basically for different applications of higher volume and lower divestment.
Yeah, so you mentioned the walkthrough. I've seen that scenario kind of in the future that people would just walk down a hallway on their way to the terminal, and these would be embedded in the walls and they would just automatically be scanned. How close are we to that future?
Yeah, it's here. It's the Total Recall Terminator or Total Recall type of systems are actually fielded and in use right now. I mentioned the QPS Walk 2000. It uses a lower power ultra wideband pulse, and it has hundreds of transceivers opposed to thousands. And it's doing pictures or frames at about 8 to 10 images per second. It takes you a little over a second at a normal walking speed. And in fact, it's around 3 seconds because it's actually taking pictures as you're walking in and as you're walking out. So it really does get this 360-degree image of a person walking through at a normal gait. And these systems have slightly lower resolution. And what we kind of use, I think in Europe they use it, it's a 19-cent piece. So it's a 20-cent piece with a hole drilled in it so they can kind of move it all around the body. But it's about the size of a nickel in US terms. And that allows us to see, a pretty good assortment of threats that might, are not supposed to be on people. And this really, one of the advantages of using this lower frequency is that it minimizes the divestment for lower risk applications and dramatically increases the throughput. So you can walk in with heavy clothes on, with your wet clothes, your jackets, and things that you wouldn't normally be able to go through kind of passenger screening in an airport. This is more for people coming in off a tarmac or people coming in from the wet and being able to walk through and looking, and all they really need to do is divest things out of their pockets. So this is ideal for, as I mentioned, less stringent applications like the worker screening, event screening, and other applications where You need some type of a level of threat detection, but a metal detector, cannot perform that. And we've used this technology at places like border control, where you're looking for money and smuggling of drugs and things like that, because it sees all those non-metallic objects.
Has there been any talk about using this in schools?
We actually have some juvenile detention centers we've used this in. Primarily, the technology that they're using in schools right now are what are called smart metal detectors. I think the price point, we're not really focusing on the schools at this point in time, just because they're really being serviced with a lot of these metal detector technologies that are out there right now, and then that we're at a different price point for that. But we do have some detention centers that I made, which are higher risk students that they need to be in for curfews, and they want to make sure that they're not, doing smuggling and bringing things into the detention center at night and things like that. So corrections facilities, detention centers are kind of more of our threshold there.
Well, since we seem to have already embraced this total recall scenario, what future enhancements do you see coming in the next few years?
Yeah, there's several, and it's great. I mean, it's great just now that we're kind of hitting the stride and being able to tailor our solutions for other applications. One of the things we're involved with was a Department of Homeland Security project called Scanning at Speed, and this is currently on demonstration at the Harry Reid Las Vegas International Airport. We've partnered with companies to explore the viability of automatic security operations. This is basically being able to be accepted into a basically what we call a man trap, being guided in how to get into the mission to be screened, self-triggering on the person being screened, and then if there are alarms, notification of where the alarms are so they can properly divest and try again. And basically, this will reduce several of the need for personnel at security lanes. And while it might seem far-fetched, in my lifetime, I never thought things like passport control would ever be unmanned or uncrewed. And right now, if you go to a lot of the major airports over in Europe, they actually have the systems where passport control is basically biometric read of your face and your passport to make sure you have your credentials and you walk on through. So self-screening is definitely one of the areas that we're looking at doing, and not so much. This also has applications around a lower volume type of needs for like things like data centers, where they have a very low volume of people getting into the secure area, and they don't necessarily want to staff 24/7, 360, multiple people at a security lane waiting for the occasional person that walks through. We've also, as I mentioned, been able to develop and adapt our product for many different applications tailored on our detection algorithms. And the AI really plays an important role in expanding and seeing some of those new markets. So that really is, for the future, that as new threat objects become prevalent that can't be seen by existing technologies, it's great to be able to adapt these technologies to be able to address those concerns. Some of the examples, I mentioned the soccer stadium before, and the bottles and pyrotechnics, but we've also had, expensive components, placement components in the cell phone industry, being able to focus and tailor a solution just on that. With future enhancements in AI, we're also, looking at the possibility of screening passengers with disabilities, including those, physically in a wheelchair, being able to allow them to pass through at a faster pace.
Well, this has been excellent. And thank you, Darren, for taking the time to talk with us today about this very interesting technology and kind of keying us in on the current and emerging applications for millimeter wave scanning. We appreciate your insights on this and hope to have you back as the technology evolves. And to our listeners, you can find more podcasts at podcast.microwavejournal.com. And thanks for listening.